So to put some actual context into the types of collisions, we're going to look at an abstract example of each three. So the first example we're going to look at will be an example of a perfect elastic collision. So this will satisfy both the conservation of momentum and conservation of energy. And again, don't worry too much about the conservation of energy part. We're always going to treat these as conservation of momentum because all three examples do satisfy conservation of momentum. So example one, a ball A of mass m is moving to the right with an initial velocity and velocity v. So we're not given specifics, we're just given variables. It's going to collide in a perfect elastic collision with ball B, which is initially at rest. So that one we are given a number for. If it's at rest, we know it's 0. Ball B then begins to travel with half of its initial velocity of A in the same direction to the right, and ball A travels to the left with half the velocity that it had initially. Okay. What is the mass of ball A with respect to ball B, and assume no friction or drag? First things first, let's draw out what is going on here in the system just to kind of better see how these are traveling. So I'm going to, because I'm terrible at drawing circles, just copy paste a circle right here. The pink's going to be ball A. We'll have the blue be ball B. This is ball A. This is ball B. Ball A is traveling to the right with a velocity v, which is a vector. And ball B is stationary. V equals 0. Okay. And the way I set up conservation of momentum equations is the momentum. So the momentum before the collision is going to equal the momentum after the collision. So what is the momentum before the collision? Well, it's the sum of the individual balls' momentums. So that's going to be the momentum of A plus the momentum of B. And that's going to equal after, if this is a perfectly elastic collision, we know they don't stay together. So this is going to be, we could call this initial momentum of A, initial momentum of B. This then would be the final momentum of A plus the final momentum of B. And let's figure out, well, we know from momentum equation, the momentum is equal to the mass times the velocity of an object. So in the first case, it's going to be the mass of A, or we could call it the initial mass of A, but is the mass of either ball actually changing? That's actually going to stay constant. The thing that's changing here, then, it would be their momentums. So the mass of A, the initial velocity of A, which we are calling from the problem V, but we'll put that in a second, plus the mass of B, the initial velocity of B, and that's going to equal mass of A, the final velocity of A, plus the mass of B, the final velocity of B. Well, we know let's plug in what we know about how the masses change. All right, so for the first case, we know the initial velocity of A, we're just going to call V, and the initial mass, M, or the mass of ball M, or I can't talk today. The mass of ball A is just going to be M. So M, this part just becomes MV. And then we know that the initial velocity of ball B is 0. So that's 0. So this is going to then equal the mass of A, which is just M. The final velocity of A, it tells us, so we have to kind of deduce this. It's half of the initial velocity. Oh, hang on. That's ball B's. Let's look. And ball A travels to the left with half the velocity it had initially. So if it was initially going to the right, then it travels to the left. That gives us a negative sign. And it's half of the initial velocity. So it's going to be -1/2 V. And then this is going to be plus the mass of B, which is going to be the thing we're trying to find. We don't actually know what that is. But we do know the final velocity of B. It says then the ball B then begins traveling with half the initial velocity of A in the same direction. So this is going to be 1/2 of the velocity of A, which is just going to be V. And then I'm going to solve this for the mass of B. That's what we're trying to find. So what I'm going to do then, this is going to be MV equals -1, I'll do it like this, 1/2 MV plus 1/2 MBV. And then let's add this to the other side. So you can think of this as 2 over 2, if that helps you kind of add that. I get 3 over 2 mv is equal to 1 over 2 mbv. Both have a v term, so I can actually cancel that out because I'm putting it with respect to the same velocity, so it's okay to cancel that out. I'm going to multiply the 2 to the other side, and I get that the mass of B is 3 times the mass of A, the initial ball. So it's 3 times its mass.